In the previous lecture, we introduced the matrix displacement method using the slope deflection formulation. In this lecture, we are going to offer an alternative view of the matrix method, one that facilitates its algorithmic use. Consider a beam segment. Ignoring axial displacement, we can say that the member has 4 degrees of freedom. Let's label them D1 through D4. D1 is vertical displacement, and D2 is rotation at the left end of the member. D3 is vertical displacement, and D4 is rotation at the right end of the member. For D1 and D3, we define upward as positive. For D2 and D4, counterclockwise is positive. Since we are ignoring axial deformation for now, there would be no axial force in the member. We only have shear force and bending moment present. Let's label the member end forces F1 through F4. F1 is shear force, and F2 is bending moment at the left end of the member. F3 is shear force, and F4 is bending moment at the right end of the member. We can write these forces and displacements in vector notation like this. This is called member displacement vector, and this is called member force vector. We know that force and displacement are related to each other. But what is that relationship? And how do we write it mathematically? Let's start by examining a simpler case. Consider a linear spring. If we pull it by a force, say F, it is going to displace by D. What is the relationship between F and D? We know this from basic physics. F equals K times D, where K is called spring constant, a measure of the stiffness of the spring. We can also refer to it as stiffness coefficient. So the force and the displacement it causes are related to each other via a stiffness coefficient. Let's generalize this concept by applying it to our beam. Here we have 4 forces and 4 displacements. Therefore, we need more than one stiffness coefficient in order to write the needed mathematical relationship. How many coefficients do we need exactly? We need 1 coefficient for each force displacement pair. We can pair the 4 displacements and the 4 forces in 16 ways. We can pair F1 with D1, F1 with D2, F1 with D3, and so on. Therefore, we need 16 stiffness coefficients. Writing the coefficients in matrix form, we get this 4x4 matrix, which we call member stiffness matrix. We use number subscripts to label the individual coefficients. For example, K11 is the stiffness coefficient associated with pair F1-D1. K12 is the coefficient for pair F1-D2, and so on. Let me write the first equation in algebraic form. It defines F1, the shear force at the left end of the beam, in terms of the 4 displacements and 4 stiffness coefficients. What is K11? It is the stiffness coefficient for pair F1-D1. This means if the beam is displaced in direction 1 by D1, then a force equal to K11 times D1 develops in direction 1. Similarly, K12 is the stiffness coefficient for pair F1-D2. If we give the beam a displacement in direction 2, then a force of K12 times D2 develops in direction 1. So, the total force in direction 1, which we labeled F1, is the sum of the forces in direction 1 caused by each of the 4 displacements. How do we determine the values for these 16 stiffness coefficients, you ask? We already have determined them in Lecture Essay 4.5. Let's use them here without any additional derivation. Here they are. This is our generalized beam stiffness matrix. Given a continuous beam, we apply it to each beam segment with its own L, E, and I. Since in our examples we often assume a constant EI, then the only parameter that changes from segment to segment is the length. For example, this beam has two segments. The left segment has a length of 4 meters, and L for the right segment is 2 meters. So we need to write two member stiffness matrices, one with L equals 4 and one with L equals 2. For member AB, the stiffness matrix becomes or we can write it like this. For member BC, we can write and here is its simplified version. We are going to use these stiffness matrices to assemble the system stiffness matrix, which we will then use to analyze the beam. Let's see how we can assemble the system stiffness matrix from the member stiffness matrices. At the heart of this process is the numbering of the degrees of freedom of the beam. Our beam has 3 degrees of freedom: rotation at the roller at B, and vertical displacement and rotation at NC. Let's number these 3 directions as 1, 2, and 3, and refer to the degrees of freedom, the displacements, as D1, D2, and D3. Although we know vertical displacement at C is downward, we always show our unknown displacements in positive direction. Note that I am using uppercase D for system displacements and lowercase d for member end displacements. Our objective here is to calculate the system displacements. We can write them in vector form like this. We are also going to define 3 forces, 1 force along each defined direction. So we get F1, F2, and F3. View them as applied joint loads. Here, since the beam is subjected to a single concentrated load in direction 2, then only F2 has a non-zero value. It equals -10 kilonewtons. F1 and F3 are 0 since there is no applied moment at the roller or at the free end of the beam. The system force vector, then, can be written like this. The relationship between the system force vector and displacement vector can be defined using a system stiffness matrix. For our beam, this matrix has to be 3 by 3, since there are 9 force displacement pairs here. We determine the elements of this matrix by adding the related elements from the member stiffness matrices. Let's examine the correlation between the degrees of freedom of the system and those of the members. D1 of the system is the same as D4 of AB and D2 of BC. D2 of the system is the same as D3 of BC. And D3 of the system is the same as D4 of BC. The same correlation holds true between system and member forces. With this in mind, let's see how we can determine K11 for the system. This is the system stiffness coefficient for pair F1-D1. This displacement force pair matches pair F4-D4 for member AB and pair F2-D2 for member BC. Put it differently, system stiffness for pair 1-1 corresponds to member stiffness for pair 4-4 in AB and member stiffness for pair 2-2 in BC. So we can write K11 equals K44 of AB plus K22 of BC. Since we already have defined the member stiffness matrices, we can write this equation tells us that both AB and BC contribute to the stiffness of the entire beam for pair 1-1. This should be intuitively obvious as direction 1 is shared between the two beam segments. In contrast, say for system pair 1-2, segment AB makes no stiffness contribution since the pair does not have a corresponding pair in AB. That is the case since degree of freedom D2 is not located at an end of segment AB. Therefore, system K12 is defined using K23 of BC only. Since system pair 1-2 corresponds to member pair 2-3, we can write. Similarly, system pair 1-3 corresponds to pair 2-4 in BC. So we can write system pair 2-2 corresponds to pair 3-3 in BC. System pair 2-3 matches pair 3-4 in BC. And, by the way, stiffness matrices are always symmetrical. I'll explain the reason behind this in another lecture. For now, let's take advantage of this property and populate the rest of the matrix like this. Here is our system of equations. We know the elements of the force vector. They are. Therefore, the only unknown is the displacement vector. Solving for it, say, using Gaussian elimination method, we get knowing the system displacement vector, we can easily determine member displacement vectors. Member AB has 4 displacements. 3 of them are 0, and the 4th one is the same as system displacement D1, which is the rotation at joint B. So we can write for member BC, we can write or knowing the member displacement vectors, we can easily determine member force vectors. For AB, we have making the substitution for the displacement vector, we get. So member end forces are. For member BC, we can write here are the member end forces for BC. Knowing the member end forces for AB and BC, we can determine the support reactions. Like this. In this lecture, we illustrated the process of formulating the system of equations for analyzing continuous beams subjected to joint loads only. We will expand the formulation to cover beams subjected to distributed and concentrated loads in the next lecture. For now, here are a couple of exercise problems. See if you can analyze them using the matrix displacement method as was explained in this lecture.